So it's fantastic to be here. Can you hear me with the microphone? Is it okay? Okay. And well, of course, my main task for today will be to highlight some of the difference between polynomial and transcendental dynamics. It will be a more elementary and descriptive and survey talk with respect to many other talks in the conference. And the second main task, as you may have understood, will be to finish in time for lunch. So, okay. So, first of all, why polynomial and not rational dynamics? So one can debate a little bit about it, but I find that in one variable there are four main characters, four main types of functions that you can study. You can study polynomials that you can see either as entire function from C to C, or that you can extend naturally to the Riemann sphere C hat. You can study rational maps, which are naturally acting on the Riemann sphere. You can study transcendental entire functions, which naturally act in the complex plane. And you can study meromorphic maps, which are portions of transcendental entire functions, and that naturally act from the complex plane to the Riemann sphere. So somehow there are similarities either in the rows or in the columns. So polynomials share similarities with transcendental entire functions, and they share similarities with rational maps. Transcendental entire functions share more similarities with polynomial than with rational maps, and meromorphic maps share similarities both with rational and transcendental entire. For example, both rational maps and meromorphic maps can have Hermann rings, while polynomial and transcendental entire functions cannot have Hermann rings. Now, I will stick to no-pole situation, okay? So to the situation, I will study transcendental entire function, and I will make the parallel with polynomials instead of rational maps to make the analogy more clear. So what are the first obvious differences between polynomial versus transcendental entire dynamics? The first, to me, striking difference is that transcendental maps have an infinite topological degree. So points have infinitely many preimages, not just finitely many like in the polynomial case. And the second observation is that C is not a compact space. Now, in the classical theory of dynamical systems, a lot of study of dynamical systems is on compact spaces. So the fact that our transcendental maps act on a non-compact space, I think is one of the key immediate differences that you see between polynomial and transcendental dynamics. And finally, infinity is an essential singularity. So in infinity, you really have a lot of possible behavior, a chaotic behavior given by Picard's theorem. I will get more to it in one of the later slides. And so what we really concentrate on? We will concentrate on the fact that when you look at transcendental maps, you suddenly get new singular values. So somehow the local behavior has new features that do not appear in polynomial dynamics. Then we will look at some new features that appear in the Fatou set, which are Baker and wandering domains. Some new features in the Julia set. The Julia set in particular will be unbounded exactly because infinity is an essential singularity. Okay. And this will make, in many cases, we will see that the Julia set is equal to the entire complex plane. So somehow the structure of the Julia set, which is very interesting in some of the cases, becomes, let's say, well known in the case where it's equal to C. And here is one of the points where the escaping set comes into play. So in some cases, you don't study anymore just the Julia set, because it may be, for example, the entire complex plane. You start looking at proper subset of the Julia set. There are many subsets that you can choose, and one of these is the escaping set, which is a set of points whose orbit converge to infinity. And finally, I will say just some words, just one slide about parameters. Let us start with the new types of singular values that we can have. So the singular values are what? Are critical values, asymptotic values, and any accumulation points of any of these two types of values. What are critical values? Critical values are the images of critical points. What are asymptotic values? They are values for which there is a curve going to infinity, whose image is a curve converging to the asymptotic value. So somehow we could say that asymptotic values are values which have some of their preimages at infinity. Now, in polynomial dynamics, you have finitely many critical values, and that's the end of the story. In transcendental dynamics, you have critical values, asymptotic values, and you can have infinitely many. And for many purposes, it's necessary, it's important to define as singular values also the accumulation points of these two special values, which are critical and asymptotic values. And there is a lot of theory about the theory of singular values or singularities of the inverse function for transcendental functions. Let me show you in terms of coverings what is happening, okay? If you have a regular point, so a point which is not a critical value, an asymptotic value, or an accumulation thereof, look at its preimages. I only drew finitely many for obvious reasons, but all the preimages of a small neighborhood of your regular point are simply connected neighborhoods. If you take critical values, you may have as many simply connected preimages of your neighborhood as you wish, at least one of them is mapped D to 1 with a covering which is equivalent to the map Z goes to Z to the D. It's a covering of the punctured disk where the puncture is your critical value. This is very interesting. Well, no, let me figure out where it is. It must be here. Yes. Let's hope it was a one-time issue. So critical values are the images of at least one critical point. So when I take the preimage of a neighborhood which is centered at my critical point, my covering will not be 1-to-1. It will no longer be a homeomorphism. It will be a D-to-1 map. And finally, we have the new entry, which are asymptotic values. So asymptotic values, when you take a neighborhood of them, they can have as many 1-to-1 preimages as you want. They may have some critical preimages, so there may be some disks which are mapped D-to-1, but at least one preimage of your neighborhood is going to be an infinite set, morally a half plane. And the covering from your infinite set to your small disk is infinite to 1. So this is really like, you can really think about 0 for the exponential map. The preimage of a neighborhood of 0 is a left half plane. And this left half plane is mapped infinite to 1 to a neighborhood of your asymptotic value. So what is the property of this set of singular values? The property is that if you remove all the preimage of your singular values in C as domain, and you remove all of the singular set in C seeing as a target space, what you get is an infinite degree unbranched covering. So somehow, the interesting dynamics in the map is very related to how many singular values you have, what type of singular values you have, where they are in the plane, and their dynamics, the orbits of your singular value. This is why it's usually important to define the postsingular set, which is just the union of all the forward images of all your singular values. You will, so this is called the postsingular set, and it will appear in some of the theorems. It's analog of the post-critical set you have for polynomial. And if for example, your postsingular set is nicely behaved, on the complement of this is forward invariant, and on the complement of the postsingular set, you have that your map, you can take preimages of disk, and all preimages are univalent. So let me talk about some special classes of transcendental entire functions, because they will appear in the talk by Chris Bishop and Lasse Rempeg, which will be the continuation of this course. So two of the important classes of transcendental entire function that one can study in terms of their singular values are the Speiser class S, which is the class of entire transcendental functions with finitely many singular values, and the Eremenko-Lyubich class B, which is the class of entire transcendental function with bounded set of singular values. So you may have infinitely many singular values. They may accumulate. They may form a continuum, an open set. No, not an open set, a closed set, but a set with non-empty interior. They may form whatever they want, but they are all contained in a disk. And finally, let me mention, in terms of parameter spaces, one of the most studied class of transcendental maps is the exponential family. So I would say the exponential family f of z is equal to e to the z plus c, where c is a parameter, can be really seen in many respects as an analog of the families of unicritical polynomials. You can do, for the experts, you can do a lot of combinatorics. You can study the parameter space. There are many, many similarities between the specific family of transcendental entire function, the exponential family, and the families of unicritical polynomials. You can define fibers, you can do a lot. I'm sorry I will not have the time to go over it, but there is a beautiful paper by Hennenfent and Schleicher which makes a parallel about some theory of parameter spaces for unicritical polynomials, including fibers, and some theory for parameter spaces of the exponential family. One of the most interesting things that appear in transcendental dynamics are new types of Fatou components. So let me remind you what is the Fatou set. Since I'm the first person here to talk about the Fatou set, I would have never bet, but I know you all know what the Fatou set is. But it's a set of points near which, in a neighborhood of which the iterates form a normal family, which means, technically speaking, that the sequence of iterate Fn, for every sequence in the sequence of iterates Fn, you can find a convergent subsequence. So it's a bit of a tricky definition. One needs to work with it before one truly understands it. There are books written on normal families, you know. But what you should think of, in the remote case you haven't seen this before, is the Fatou set is the set of points which kind of move together with a neighborhood of them. All points nearby in some way behave similarly to them. Now, what is the main discrimination between Fatou components? The Fatou components can be periodic, which means you have, okay, what is a Fatou component? A Fatou component is a maximal connected component of the Fatou set. The Fatou set is open by definition, and it's split into connected components. You may have just one of them, you can have infinitely many of them. And what can Fatou components do? Before we go to the fine-tuning, okay, what can they do as sets? They can move around and come back to themselves, and then they're called periodic. They can move around, and then coming back to some points, some component in their orbit, and then they're called pre-periodic. But they can start moving around the plane, and now they're coming back to themselves, and then they're called wandering domain. Questions? Maybe not yet. I know for many of you this is well-known material, but maybe one or two slides will be new. Okay, what was one of the main results in the 80s was that Sullivan proved that for polynomials, all Fatou components are periodic or pre-periodic. So we can forget about components wandering around and never coming back. They always come back to themselves or to another component in their forward orbit. And once you know that they're periodic or pre-periodic, you can use the machinery of the Wolf theorem to show that you can classify them. Okay? Now, you classify the invariant components, which means the components which are mapped inside themselves. And of course, if you have a component which is periodic of period P, this is the same. This is like understanding what happens under F to the P. And if you have a component which is pre-periodic, it's like understanding what happens after it made these few steps and then starts coming back to its image. And what are the types of Fatou components that you can have for polynomials? We all know them. Most of us know them. You have the attracting basin of infinity, which is the only one which is possibly not simply connected, and on which they iterate. So if you take a polynomial, when you go very close to infinity, what is going to happen? Your polynomial is a to the d, a d, z to the d plus lower order terms. When you go near infinity, it's basically a monomial. So near infinity, your polynomial is z goes to some constant times z to the d. So you are increasing your modulus. What does it mean? It means that if you go in a small enough neighborhood of infinity, you are trapped in that neighborhood, and you're going to converge to infinity. So really near infinity, there is no interesting dynamics that can happen, and you can then extend this set, making it maximal. This is a attracting basin of infinity. Then what other types of Fatou components can you have? Invariant again. So you should imagine a component mapping into itself. You can use the maximum principle and see that they're simply connected. And once they're simply connected, you use the super powerful Riemann uniformization theorem, and it's like having a map from the disk to itself. And then we have the Wolf theorem, which tells us that either you are a rotation, which is a Siegel disk in our case, or you converge to a point of the boundary, and then we have something which is called the parabolic base, or you converge to a point in the interior. And this is what is called an attracting. So why are we talking about the classification of Fatou components for polynomials? Because the classification of two components for entire function, well, this is a picture. Tracking Bayesian, you converge to a point inside. Parabolic Bayesian, you converge to a point on the boundary. Rotation domain, you basically rotate around some center in your domain. And these are some pictures. The first one is a picture of the black one is a tracking Bayesian of infinity. The second picture is the Duadis rabbit. And basically, the center of the picture, which is the belly, maps to the smaller set which touches with it and which maps to the slightly larger one and then maps back. So this is a period 3 attracting Bayesian. This is the cauliflower. Everybody converges to. This is a picture. Yes, everybody converges to this point in the boundary. And this is a, I don't know whom I should credit for this picture. I suspect it's Arnaud Cherita, but I'm not 100% sure. So here in one of these two disks, you can choose whatever you like. You have rotation inside. Your map is conjugate to it. Now, why are we spending all this time on Fatou component for polynomials? Because for transcendental entire function, the classification is almost the same, except for 3 main differences. First of all, there can be no attracting Bayesian of infinity, because infinity is an essential singularity. So there is no way you can have a neighborhood of infinity which is mapped inside itself. And so since this is no longer possible, you can have other types of Fatou components which somehow come near to infinity. And they are called Baker domains. I will give you the definition in the next slide. So you can have new components on which the iterates tend to infinity, which are no longer attracting Bayesians. And you can have these famous wandering domains, which were excluded by Sullivan in the polynomial. What are Baker domains? Baker domains are periodic Fatou components, exactly like the ones we had for polynomials, on which the iterates tend to infinity and which are not attracting Bayesian. Well, you can state it in 2 ways. Either you say that Baker domains are periodic Fatou components for transcendental functions on which the iterates tend to infinity, because you know immediately they cannot be Bayesians if it's a transcendental function with an essential singularity, or you just say that it's a periodic Fatou component on which the iterates go to infinity and which are not attracting. Questions? So I will try with the pointer. Okay, so what I think is interesting is that at very first sight, when you get this definition, what do you imagine? You imagine infinity and some Fatou component attached to infinity in which the iterates converge to the boundary. What is your first intuition? The first intuition that this is just a parabolic Bayesian with a parabolic point at infinity. This intuition is wrong, okay? You can have, so what is the specificity of being a parabolic Bayesian? It is that you are conjugate to the map z goes to z plus 1 on a half plane. And this is not always the case for Baker domains. In fact, you have several different dynamics that can happen on your Baker domain. So we have a classification, somehow the classification of Baker domain is a subclassification inside of the classification of Fatou component. I think this is interesting. And you have several normal forms. I will show it by picture. Another thing which is very interesting is that all Baker domains are simply connected. And what is even more interesting is the proof of the fact that Baker domains are simply connected. So you may have seen it or not in your life, but if you have a bounded Fatou component, for simplicity it's bounded, but it's enough the limit functions are bounded, then you can use the maximum principle to see that this Fatou component can have no holes, and this gives you that all Fatou components with bounded limit functions are simply connected. Yes?
I assume that the model that you were referring to is as a map from the upper half plane to itself?
I think it's the right half plane to itself.
You think it's the right half plane?
I think it's.
I don't. I think it's the upper half plane.
Because right.
Oh.
I think I'll show you the picture in a minute, and maybe this will clarify.
Depends on the model.
It depends on the model you choose. Yeah, I think if you could do it on the upper half plane, but then your models would be z goes to z plus I and z goes to z plus minus 1. It's exactly the same. You could take it. It's totally up to you. Or you can take. Yes, and the plus minus 1 gets in the 1. Well, okay. Let us solve the problem. Okay, so you can imagine this. So there is a conjugation on a proper subset of your Baker domain. You're either conjugate, so you bring, I'm slightly cheating, but not too much. You have a proper subset, an absorbing domain in your Baker domain that you can map to a right half plane. It's slightly cheating again, but morally it's true. So either you are a translation parallel to the boundary, which is z goes to z plus I, both directions are allowed, or you are a map which moves away from the boundary as a translation. This is the z goes to z plus 1, or it's basically you are the source and everything is spreading from this source and then converging to infinity. Okay? And of course, just as you say, as model you could take the upper half plane, and again your model map would be translation parallel to the boundary, moving away from the boundary, or starting from a source and going towards infinity. The middle one is technically, it's a bit complicated. So what happens is that the second conjugation is not on the half plane, but it's, as far as I understand, on a kind of sector, and it's as a subset of C. So I'm slightly cheating here with this. This is true. I think so. I understand. I understand so. I can check, but I understand this is. So, and one thing that I think is interesting for this specific audience for you is that there is some study of deformation spaces of Baker domains, which has been done by Fajay and Henriksen. And some of these Baker domains have infinite deformation space, and some of these Baker domains have finite deformation space. So it depends really on the type of Baker domain that you have. So they are not only different from the point of view of dynamics, that your normal form is different, they're also different from the point of view of deformations. So when you, and now I'm not going to go into details because you have a course on Teichmüller theory, but essentially you can put a conformal structure on your Baker domain, and if your Baker domain is simply parabolic or hyperbolic, you can deform it in infinitely many ways. You can find an infinite dimensional deformation space just of the, so as far as I understand, the Teichmüller space, the whole space of deformation of your function f depends on all the way that you can deform your function on completely invariant subset. If you have a Fatou component, you consider its grand orbit, so all of its forward and backward orbits, you get a completely invariant set. So for every for the Julia set on one hand, and for every grand orbit of Fatou components, you can study the deformation which happen on these Fatou components. And if your Baker domain is doubly parabolic, then you can find that the deformation space is finite dimensional, while if it's any of the other two cases, it's actually infinite dimensional. Ready to go for wandering domains? So wandering domains are, as we said before, Fatou components which are not pre-periodic. So they move around and they never intersect the original one. And they can, the first rough classification of wandering domains is in terms of their so-called limit functions. I don't want to go into defining limit functions, but essentially wandering domains can be domains which escape every compact set. Well, in fact, it's more correct to say that they are domains on which their orbits all tend to infinity. They can be oscillating, so some points, some limit functions, under some sequences of the family of iterates, you go to infinity, and then some subsequences you go to finite points in the plane, or you could have that under somehow all orbits stay in compact sets. So escaping is if all your orbit converge to infinity. Orbitally bounded is if all the orbit of each single point stays in a compact set, and oscillating is neither of the two. You can really imagine domains moving close to infinity, coming back to a compact set. Necessarily, they need to get smaller. Moving, well, no, not necessarily. I said something wrong. Coming back to some orbits, coming back to some compact set, and then going to infinity again, close to infinity again. And so as we have seen, for polynomials and more precisely for rational maps, there are no wandering domains, which means that alpha 2 components are pre-periodic. And it's interesting to note, again, going back to the deformation space, we will have a final slide on that, is that you can show that if you have functions with finitely many singular values, they have no wandering domain. You can show more. You can show that if you have functions which are in this class of bounded set of singular values, you cannot have wandering domains escaping to infinity. And it was kind of expected, I think, that maybe functions with bounded set of singular values do not have wandering domains at all. This was not clear, and in fact, it's false. They can have wandering domains, just they need to be oscillating, and we will see some example of that. Now, there is a big question, which is, can we have wandering domains from which the orbits have no subsequence which goes to infinity? So do these orbitally bounded wandering domains actually exist? And I don't even know what is the feeling of the expert about whether they should exist or whether it should be possible to prove that they don't exist. You see, the proofs of classes of functions where we don't have wandering domains, the fact that we don't have wandering domains in the class S is because essentially you can show that if you are in class F, S, your function has a finite deformation space, and then you can use something very similar to Sullivan's proof, deduce that there are no wandering domains. So this is one of these very indirect proofs, and it's not really clear where the fact that you have an essential singularity interferes with this existence of wandering domains. So the role of the essential singularity in the orbits of wandering domains is not completely clear. Why they appear in the transcendental setting and not in the polynomial setting. The transcendental singularity must have something to do with it. All the examples that we have do accumulate on the essential singularity, but the role is not, in my view, completely clear. So big question in the field, I think it's one of the main in transcendental dynamics, is whether these wandering domains, let's say with bounded orbits, exist. You have to be a bit more careful to formulate precisely. And I think, so one of the breakthroughs in wandering domains was that you can have wandering domains in this class of functions with bounded set of singular values. And of course, they cannot go to infinity because we have a theorem by Riemann-Lubitsch that says that you cannot. But you can have some which moved close to infinity and then come back. And there have been examples constructed very recently by Bishop first using a technique called quasi-conformal folding. He will tell us a bit more about it. And then there are examples by Marty Pete and Shishikura, which, if I understand correctly, are done using approximation theory. And what I think is interesting is that wandering domains can come basically in any flavor that you like. So they can be simply connected, infinitely connected, bounded, unbounded, locally connected. The boundary can be lakes of Wada. You will see this in David Marty Pete's talk. And just to mention it, they can go to infinity as fast as you want them to go to infinity. So I'm sorry if somebody is missing from the citations. I tried to collect the references, but there are many, 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 many examples of wandering domain, like Verweiler did several examples, and there are many, many examples of wandering domains. This is just a few of the people who worked on wandering domains. No, I think you can have infinitely many. I'm pretty sure you can have infinitely many. Because when you do approximation theory, if you do it carefully, I think you can get infinity. So one of the main tools to construct wandering domains which go to infinity is to use approximation theory. You prescribe your map to move a certain set to another set and so on. And the tricky thing is to make sure that your sets do not connect all together to give you, for example, a Baker domain. But let's say that approximation theory is a very natural tool to construct wandering domains going to infinity, and you can basically, you have a lot of freedom in prescribing how many orbits you want, grand orbits you want, and a lot of how the internal dynamics works and things like this. Yes? Okay, so even just we have somebody who constructed examples with infinitely many. Yes. Oh, so yours is also quasi-conformal. Okay, thank you. I was not sure. Thank you. And we can say a lot of things about wandering domains, but I think we should move on to the Julia set. So the Julia set for transcendental entire function has a lot of differences with respect to the Julia set for polynomials. The very first observation is that Julia sets are unbounded, and this everybody can understand, because no matter how elementary, because if you take a neighborhood of infinity, you have Picard's theorem, which tells you that the image of this neighborhood of infinity will spread over the entire complex plane, except possibly for one point. Since the Julia set is completely invariant, this means that in every neighborhood of infinity, you will have pieces of the Julia set. And yes, you will also have preimages of every photo component that you have. Okay? But really, to see that the Julia set is unbounded of a transcendental map is elementary. Another difference with polynomials is that the Julia set contains points whose iterates converge to infinity. Always. Eremenko, 92. Beautiful construction using the Riemann-Walleyron theory. The Julia set always intersects a set of escaping points. And this is dramatically different from the case of polynomials. Look, we know that if you are converging to infinity, there is one way, the attracting basin of infinity, period. Another thing which is very striking in my view is that the Julia set can be all of the complex plane. And then you see, once it's all of the complex plane, when you want to study geometries of these functions, you kind of want to find finer sets inside the Julia set that you can study. And this is where the set of escaping point will come in. And then another thing which is very interesting is that we're used to think that for every period, there are finitely many periodic orbits. This is no longer true. Like here, when you look at solutions of the transcendental equation, actually there is more geometric proofs. You can see that there are infinitely many repelling periodic orbits of any period bigger or equal than 2. And it's still true that the Julia set is the closure of all repelling periodic orbits. Just for every period, you have infinitely many. They tend to have large out of dimension. Now, this is more of a feeling than a theorem, okay? Clearly, when your Julia set is equal to C, it has out of dimension 2. But also, in many cases, it consists of curves that accumulate on each other in such a way that the resulting set, together with the endpoints, has out of dimension 2. And another thing that may interest some of the audience in this room is that, for example, in this class of sets with bounded set of singular values, they are not locally connected, never. And this, you can see, it reflects in local connectivity not being true for the parameter space of the exponential family. But, so there is a lot you can say about Hausdorff dimension, but let me talk a little bit about local connectivity. So what about local connectivity of transcendental Julia set? I need to introduce a set that is called the spider web. So I read the definition, and then I will try to give you an idea of what this is. A set is a spider web if it's connected, and there exists a sequence of bounded simply connected sets, one contained in the other, an exhaustion of C, if you want, by disk, topological disk, whose boundary is in your spider web. So let me try to draw you a picture, just one, the only time I will use the blackboard. You could imagine a spider web to have, can you see if I write here? Well, if you don't see, complain. So you can take sequences of nested open sets, and like more and more, exhausting to form all of C. These are just simply connected open sets, and the boundary is in your spider's web, and somehow they must be connected to each other. So I'm drawing these simplified lines so that it really looks like a spider web, but so these kind of circles need to be connected to each other in order to form a spider web. And you can have more stuff, like here you can have a full annuli with holes. I mean, the structure is more complicated than this, but there is this underlying structure which has the shape of a spider web. And I will repeat this when I go on to studying the escaping set. But what I think is interesting is, well, there are many results about local connectivity. I will go over some of them later, but look, it's very interesting to say that Osborne proved that if the Julia set is locally connected, then it is a spider web. Now, you cannot see it at this point. I will say it later, but if your Julia set is a spider web, you can show that your function cannot be in class B. So Julia sets of functions in class B cannot be locally connected, to my understanding. Now, there are more results that you can say about local connectivity of transcendental Julia set. And I think the first ones were by Baker and Dominguez. And they tell you that if you have an unbounded invariant for two components, then the Julia set cannot be locally connected. How does this happen? This is intuitively quite clear to understand, though more messy to make the proof. But imagine you have your unbounded for two components, and imagine for 1 second that infinity is accessible, so that you have a curve in your for two component going all the way to infinity. Infinity has morally infinitely many preimages as itself. So the preimage of this curve, if it's completely invariant, will be a lot of other curves which are also in your for two component and which all go to infinity. And then you will keep taking preimages and preimages. And what will happen is that you will have a structure with a lot of curves accumulating on each other near infinity, which will create something like a comp structure. So this is kind of the intuitive idea behind showing the Julia sets of when you have a completely invariant for two components are not locally connected, and has been used also to show more results. Like this, yes? Well, no, you don't spoil my talk later. Okay. Okay. So I know there are papers about topological models, but I never read them. So I am not qualified to answer this. No, thank you. I think there are topological models even when the Julia set is not connected. Well, on all these Pinchet Cantor bouquet work. I'm just not an expert on it. I'm sorry. Okay. Now, since we had a spoiler, let me comment on that. So in this paper that I was mentioning in the very beginning, by Rempe and Schleicher, it's called bifurcation loci of quadratic maps in the exponential family, or something, some neighborhood of this title. They show, using, if I'm not wrong, ideas of Divani, that the parameter space for the exponential family, so the Mandelbrot set is kind of clear in everybody's mind. If you go to parameter space for the exponential set, you can kind of imagine a Mandelbrot set on which all the hyperbolic components are unbounded. And for each period, you have infinitely many components, which nest into infinitely many components. I mean, something like this, okay? So basically, you get kind of a picture similar to what I was describing, with a lot of curves tending to infinity and accumulating on each other, breaking local connectivity miserably. And now, local connectivity is a very strong conjecture, much stronger than the density of hyperbolicity conjecture. And somehow, the question is local connectivity the right thing to look at when we look at transcendental maps? And there are ways to restate the MLC conjecture in terms of these fibers. There must be somebody talking about fibers in this conference at some point. And restating it in terms of fibers, you can find two very similarly, formally and conceptually, conjectures which put in relation the MLC conjecture with the density hyperbolicity on one hand, and this mysterious fiber conjecture with density hyperbolicity for the exponential family on the other. Is this better? Great. Okay. So let me say a couple of words about the escaping set. The escaping set are just the points whose orbits converge to infinity. For polynomials, if you go to infinity, you do it in the basin of infinity, period, end of the story. For transcendental maps, you can go to infinity in the Fatou set or the Julia set. We have already seen how you go to infinity in the Fatou set. You are in a Baker domain, which are periodic components on which you tend to infinity, or you are in one of these wandering domains which converge to infinity, the escaping wandering domain. What is interesting is what happens when you go to infinity in the Julia set. And here you have very different structures depending on the class of functions that you consider. So you remember the definition of spider web, more or less? If your function is very small order of growth, so, well, I'm not getting into it, grows very slowly when you go to infinity, then your escaping set is a spider web. And then you have a completely different scenario. Okay, so spider web, you can imagine like circles connected by other stuff. If you are of finite order, your escaping end in class B with bounded set of singular values is a completely different scenarios. Your escaping set consists of curves called hairs of rays, which have many similarities to the external rays for polynomials. Many similarities, not from the topological point of view, because external rays for polynomial form altogether the attracting basin of infinity, but a lot of similarity from the combinatorial point of view, whatever that means if you're not an expert in combinatorics for polynomial rays. And then this assumption of finite order, this assumption of finite order can be dropped. So this is really an assumption on the geometry of the function being finite order, okay? It means that, well, you grow to infinity in a certain way. You grow at a certain rate when you converge to infinity. This, I would like to say, function theoretical assumption can be dropped and substituted by the dynamic assumption that the singular set is bounded to transform these curves, these hairs of rays, in some connected sets which are no longer curves but morally share all of the properties of your rays. Unfortunately, we don't know whether these three are the only possibilities that can happen. You can generalize this a bit when the singular set is unbounded, but the picture is not completely clear. But you see, there is a big gap between functions with very small order of growth and functions with bounded set of singular values. There are many, many functions left behind, and we don't really know what happens, to my understanding. So let me skip a lot about spider webs and Guadi-Hubbard landing theorem. Let me just show you one picture, which is about, these are some rays. Now, this is difficult to interpret, okay? Because the ray structure is visible but unclear. A ray is any curve which starts from here. This is the exponential family, and this is a picture about the exponential dynamical plane. And you have rays which are curves, they all start here on this line. And then they start moving out, separating from each other, and starting to nest in all these curves. And eventually, in this picture, they land at all the endpoints that you can barely see. And here, the other picture, which is more messy for a good reason, that the Julia set is equal to C. You can see that these rays, these escaping points, are dense in the Julia set, and so all this ray structure become dense in the complex plane. The very last thing that I want to say is something that I think is, again, interesting for participants in this conference, and there are a couple of words about parameter spaces for transcendental maps, and more precisely, for transcendental maps with finitely many singular values. So looking at, let's say, natural parameter spaces for entire functions starts with a weird definition, which is the definition of quasi-conformal equivalence. If we take a function, now we need a bounded set of singular values for the moment. Well, let's say we fix bounded set of singular values. And you take a function, and you can define the set of functions which are quasi-conformally equivalent to her, which means, let me read you the formula, and then let me tell you what it means, which means that it's a set of all entire functions G. I put in B, but it's not necessary. It does not necessarily, it follows from the definition, that you can see as you take a homeomorphism, then you apply F, then you take a different homeomorphism, and this is your function G. Okay? So it is like a conjugacy, but you take, instead of taking phi and phi minus 1, you take two different homeomorphisms, fixing infinity. Fixing infinity, you can relax this in other settings, but it's important in this case of entire transcendental functions. And what should you imagine? You should imagine, just look at it locally. You have a neighborhood, and your function sends this neighborhood to another neighborhood with some topological property. You remember all the covering stuff that we did in the beginning? Now, you change to have G, you change coordinates to go to a different neighborhood, but it's really a homeomorphic change of coordinates, QC. Well, again, like Hubbard said, you need to deal with QC versus homeomorphisms, but For us, it's QC. So you have a QC change of coordinates on your neighborhood, which brings you to the neighborhood in which F is acting. F does whatever she does with critical values, critical points, whatever she does. And then you do again a conformal change of coordinates. So somehow the local structure of your covering is not really changed, okay? If you had the critical points for F, this will create a critical point for G of the same degree. And there is this magic theorem. Well, it's still magic for me. It may be obvious for the authors, but there is this magic theorem that if you take a function with finitely many singular values and you look at this MF, which a priori is just a set of functions, then suddenly you get a complex manifold of finite dimension. And this is the key step to show that there are no wandering domains for maps with finitely many singular values, and you can show the Fatouche-Chicoor inequality like this is, and you can start studying these spaces. This is something that has not been done a lot, but I think should be done, will be done in the next few years. Let me conclude with another very surprising theorem which relies on this concept of quasi-conformal equivalence. It's something that Lasse calls a rigidity theorem. Lasse-Rempe, it's a theorem by Rempe, and it tells you, well, let's not assume that you have two functions which are quasi-conformally equivalent everywhere. Let's just say that they are quasi-conformally equivalent near infinity in a precise sense. So quasi-conformal equivalence, again, it's not a conjugacy because you have two different maps, not one map and its inverse. But if they are just quasi-conformal equivalent, so if there is just this kind of relation between the two maps, we can actually deduce and construct a conjugacy on a specific subset of the Julia set. The points which always stay in a good neighborhood of infinity. And I'm sorry I don't have 15 hours to talk about parameter spaces, but that's it for today.
Thank you, Anna, for this very nice introduction. Are there any questions?
Anna, your last theorem. Open?
No.
What I this set is not open. Okay.
No. Okay. Yes. Sorry. Let me repeat the question for the online participants. The question is whether the set on which you get your quasi-conformal conjugacy is open, and the answer is no. Usually, so in the class B, you can imagine for a moment that your Julia sets consist of these rays which accumulate on each other and form the so-called counter bouquet of rays. And what the conjugacy holds on the set of points on these rays, which form the Julia set, or their endpoints, which always stay in a sufficiently good neighborhood of infinity. So it's really, can I write it down? No. It holds, I think, Lasse is online, so if he is listening and I say something wrong, he can correct me. It holds on this set. There exist are such that the conjugacy holds on the set JR, which is the set of points for which all iterates have modulus bigger than R. Was that the question? Did I answer?
Okay, thank you. So it's a closed set of measure zero. What is it?
Excuse me?
Is it a closed subset of measure zero? What do we know on this set? It's a subset of the escaping set, right?
Yes.
Or maybe not.
It looks like the intersection. If you put an equal here, it looks like the intersection.
It's not. Okay.
Of like the intersection of countably many sets which are closed. It looks like that, but it's not maximal. I mean, you can extend it a bit. It holds on this set for sure, but it's not maximal. So the maximal set, I'm not sure if it's open or closed or anything. Does this make sense?
So I don't know whether the question was about the quasi-conformality. So I mean, it extends to a quasi-conformal map on the whole plane, but the conjugacy relation only holds on this closed nova dense set, which may have positive measure or may have zero measure.
Any other question? remote participants or here? No?
There was a brief discussion in the comments, which Misha suggested we might summarize. So there was a question about the singular values, whether there's a relationship between the behavior of the singular values and the wandering domains. And Walter pointed out there's this example of Shishikura and Kisaka, who constructed wandering domains where the only critical values and all of those actually map after one step to a fixed point at 0. So there's no obvious relationship between the behavior of the critical values or the singular values and the wandering domain.
Yeah, I did not talk about relation between Baker domains and wandering domains with singular values because it's really a mess. What I think is the most interesting relation, okay, Lasse, I should look at you there. Okay, so what I think is very interesting about the relation between wandering domains and singular value is that all those its limit function on the wandering domain must be accumulation points of the post-singular set. I think this is true. It was by Bergweiler and a lot of other co-authors, and I have it written down, so I'm politically correct. Not, well, in the substantial sense, not in the superficial sense. Okay, it's Bergweiler, Aruta, Krite, Meyer, and Terglain, and they say that all limit functions are in the derived set of the post-singular set.
And well, just to comment, Lasse, sorry, it's really confusing. So just to comment on Lasse's comment, I think it's not totally correct to say that wandering domains can do whatever without a relation with a singular set, because the post-singular set needs to kind of follow the orbit of the wandering domain too, not only at the limit. So
Nuria, well, Fageia, Karpinska, Harke, and Baransky have several papers on the relations between singular values and wandering and Baker domains, and essentially, depending on the size of your wandering or Baker domain, your post-singular set needs to be closer or can be a little bit farther apart than, but it's complicated to state. It deserves a talk on its own. Yes. So this is why I did not state it about it, sorry.
No, sorry.
I think it's fair to say it's a little bit, the relationship, there is a relationship, but what exactly it is a little bit mysterious.
Yes.
So maybe I may advertise this question where I think we still don't know whether you can have a function with a compact post-singular, with a compact singular set on which the iterates actually go to infinity uniformly, whether you can then have a wandering domain or not. I mean, it would have to accumulate, go to infinity, be one of these oscillating ones. But it's sort of very unclear whether to expect such examples or not, I think.
Okay, so are there any more questions? Kostya.
Yeah, so following on this, is there any positive Fatouche-Shikura type results which includes Baker and wandering domains and count of their grand orbits in relation to a singular number of singular
Not that
points?
I know of, because I think one of the main points in the Fatouche-Shikura inequality is understanding the relation of your type of Fatou component or non-repelling cycle with the singular values. And we don't understand it enough for Baker and wandering, I think, to be able to do this. This is my understanding, but maybe somebody knows better.
I'm not claiming to know better, but I think that you need infinitely many singular values anyway to have Baker domains or wandering domains, right? So
for the function.
And in most examples, you get infinitely many grand orbits of wandering domains, for example. So I think it's not quite expectable to have these kind of relations. Any more questions? Well, so I'm happy to announce that we made it 4 minutes before lunch time. So let's thank the speaker again.
Don't clap and run.